Welcome to another video for Stat 212. In this video, we're going to be looking at independence and probability versus dependence. So just kind of a big idea here with independence. So that means that if we're thinking about how things relate, it means that they don't have anything to do with one another. It means that, so like when we talk about sampling, we'll often talk about sampling being independent if the choice of one unit does not depend or change the likelihood of me choosing another unit afterwards. So if we think about that in probability, we might say that two events are independent if the likelihood of one event has no effect on the likelihood of the other event happening. So independent events are going to be things where knowing that one is true does not make me shift my mental model for the likelihood of the other being true, because I think of them as independent. They're not going to relate to one another. They're not going to be more likely to occur together than not. Okay, so if two events are dependent, that means that the probability or the likelihood of one is going to be affected, that we're going to kind of shift that likelihood knowing that the other event happened or didn't happen. So as an example, just kind of a very realistic example, let's consider the event that it's raining when you get up on Saturday morning, and let's also consider the event that your friend messages you about playing Ultimate Frisbee in the park that day. Would we consider those to be independent or dependent events? So using your intuition, you might pause for a second if you need a minute, or you might already know, we can answer this as probably being dependent, depending on your friend, I suppose. Maybe y'all don't care if it's raining or not. But I would tend to think the likelihood of playing Ultimate Frisbee when it's raining that day is probably going to go down. Or like the probability is going to be lower if it's raining, and the probability is going to be higher if it's sunny or just not raining. So for that reason, I would say these are probably dependent events. Another question that I'll go ahead and ask here is, using your intuition, do you think these are disjoint or intersecting events? This one's a little bit harder. This one I definitely think depends on your friend or not. So in other words, is it possible for both of these events to be true at the same time? Is there ever going to be a day where it's raining and your friend texts you about Ultimate Frisbee? Or are they definitely disjoint, meaning that they can't both happen at the same time? So this one, I don't know if it has a definitive answer. If I'm the friend, these are probably disjoint events, but maybe that just depends on who you are. So maybe disjoint, I'll say. If you never play in the rain / mud. I guess it kind of depends on how hard it's raining. I suppose this could be intersecting. It's possible for both events to happen at the same time if it's just like drizzling or something and maybe it stops or something. So maybe that's a storyline where we can kind of argue intersecting events here. But I feel pretty confident about the dependence, though. I definitely think the likelihood of playing is probably going to go down when it's raining, right? So I think dependence makes a lot of sense, whereas saying it's disjoint might go a little bit too far. I don't know if I would say that they can never happen at the same time. Okay, so another example with independence that I'll mention here is the gambler's fallacy. So the gambler's fallacy is believing that the likelihood of a particular outcome increases if it hasn't happened for a while. So we think about this a lot with gambling, where if you're using a slot machine, you might think that the slot machine is kind of due for a win if it's, you've played it a few times and you haven't had any winnings. Or same thing if you're like playing the lottery, that the more bummer tickets you buy, the more likely that this next ticket, well, this ticket must be a winner because I've had so many bummers in a row. Or if I'm flipping a coin, that if I've had, say, 3 tails in a row, well, now this coin is more likely to be heads because I've had so many tails in a row. However, these are all situations where you're kind of ignoring the independence of trials, right? So all these different things Maybe slot machines I'm not 100% sure about, but certainly with coin flipping or lottery tickets, your chances of winning are always still going to be equally likely if these are truly independent events. So the gambler's fallacy might kind of trick you into thinking that your likelihood has gone up when you're actually all you know is that you've just been a loser up until this point, and now you're still going in with the same odds as you did before. Um, so to kind of demonstrate this with independence, I think a really good demonstration is asking somebody to say out loud 100 random coin toss results. So so before I give anything else away, though, I'm just going to kind of present to you these two sets of coin toss results. One of these was randomly generated using R, where I randomly generated a binary process 100 times and labeled the zeros tails and the ones heads. The other is where I just asked my sister to do her very best to say 100 coin tosses, 100 coin toss results as randomly as she could. So I'm curious, if you take a second, can you tell which one is which? So you might want to pause the video if you want to think about it. But I'm going to go ahead and tell you which one is which, and I'm going to give you kind of my explanation of how you might be able to tell this in general. Notice right off the bat in this one on the left that we have, this is 6 heads in a row. And I'm going to tell you, if you were a person trying to be as random as you can saying coin toss results, would you say heads or tails 6 times in a row? And I would venture to say that there's a very little chance that you will. However, if I have a random string of 100 coin tosses, chances are that I'm going to have a string of 5 or a string of 6 at least once or twice in this 100 results, because it's not quite as unusual as you think it would be. But if you're human, your natural inclination is to keep varying, that you don't want to have too many of the same in a row because that doesn't feel random to you. But if you have enough sample points, then you really should have that once in a while. The more sample you collect, the more strings of the same results you're going to see. So if you look at my sister's result, I think she had 4 tails in a row here. Let's see. I don't know if I see anything else. I see several groups of 3, but in general, she avoided having a really long string. Whereas here on the left, we can see, again, like another string of 5 tails here. There might be another string of 5 somewhere if I'm looking carefully. It's kind of hard because we have, with the rows over, kind of ending and beginning on the new ones. But there are more strings of repeated results, certainly several strings of 4 in here. So anyway, I just thought I would kind of mention that with independence. That kind of goes along with the gambler's fallacy, just this idea that unusual things can happen by random chance more than you probably estimate they do. All right, so let's go ahead and apply finding probabilities based on intersections of independent events. So we're now moving into intersections that we're going to focus on independent events first because those are a little bit easier. So if events truly are independent, then the probability of 2 different things happening is just going to be the product of multiplying them together. So we can probably demonstrate this best with a tree diagram. So if I'm thinking about coin flip results, then I can create a tree diagram here where I flip a coin and I'm going to get heads or tails with a 50% chance for each one. And if I flip a coin again, then I'm going to have another node here where, depending on which way I went down the first time, I'm going to get heads or tails again with another 50% chance. So another heads 50% or tails 50%. And so if I ask the question, what's the probability of getting 2 heads in a row, then I would just kind of follow this path right here. So I'd go this way, and I would just multiply those probabilities together, right? So it'd be 50% times 50% means that there's a 25% chance of landing right here. So this is going to be 0.5 times 0.5 is going to be 0.25. And you might notice that that's going to be the same probability for each of these, and that's because when you're working with equally likely outcomes, which we are in this case, then all the different paths should be equally likely in the end. But this gets a little bit more helpful when we're working with non-equally likely outcomes. So let's say that I'm working with a non-fair coin, which I don't even know if these non-fair coins exist, but we talk about them in probability. Let's say that let's say that there's a 70% chance for a heads, and there's actually a 30% chance for tails. Then this gets a little bit more interesting in thinking about what's likely to happen. Oops, that should be a 0.7 there. Oops, I did it again. There we go. Got 3 on the brain there. Okay, so now we can calculate these probabilities as well, where the probability of getting 2 heads in a row now is going to be 70% times 70, and that's going to be, I think it's going to be 0.49 that we wind up down this this route. However, the other paths are going to be a little bit less likely, right? So they're going to be 0.7 times 0.3, that we get heads then tails in that order, and it's going to be 0.21. This one's going to be the opposite order, but it's going to wind up at the same probability. And finally, getting 2 tails in a row is going to be a little bit less likely. That's only going to be about 0.09. And these should add up to 100%. But we also recognize the paths are not equally likely if the outcomes we're dealing with are not equally likely to begin with. So we can use a tree diagram to kind of think about the probability of a particular sequence of events. So the intersection of 2 events, so like getting a head and getting another head, or getting a tail and then getting a head, right? That would be the intersection of 2 coin tosses. And then we can calculate the probability of that happening by multiplying them together if these are truly independent events. Okay, so let's look at a more contextual example here. So we have a hospital is trying to gather more blood donations for type O negative, the universal donor, which I think that means that if you have type O negative, you can give your blood to pretty much any blood type and it will be compatible. So it's a very kind of valued blood type to have for blood donation. Let's say that we know from a past event that about 20% of people that we ask on the street are willing to give blood. We also know that approximately 6.7% of the population has O negative blood. Let's assume willingness to give blood and type of blood are independent events, which I think that makes sense. What is the probability that a randomly selected individual will fulfill both of these events? That the person that I ask on the street is going to say yes, and that they would have O negative blood. Okay, so let's calculate it first. So the probability of having O negative blood, so this is what I want to do. I want to represent it as an intersection first. So the probability of O negative blood intersect willing to give blood is going to be the probability of each of these events. I'm used to writing a theta when I write an O. It's going to be O negative times the probability of willing, which should come out to be, I'll write it down here, should be 0.067 times 0.2. And that's going to be, I don't trust myself to do that in my head, 0.0134. Okay. So we can also represent this with a tree diagram. So again, we kind of have 2 options first, that somebody is going to be willing to give blood or not. So willing is going to be 0.2. Non-willing, I'll do like willing complement is going to be 0.08 or 0.8. And then again, the second node is going to be a different trial this time, but it's going to be independent. So it doesn't matter which way I go down, it's going to be the same set of probabilities. So having O negative is going to be 0.067, and then something else, I'll just say O negative complement is going to be 0.933, I think is 1 minus 0.067. Same thing here as well. But we're interested in this particular strain right here, right? So going this way and then going this way, and that's going to be that 0.2 times 0.067. However, if we calculate all of these, each of these different destinations has a particular probability of happening, and they do all add up to 100%. But we don't need to do that. We already found our one, but the tree diagram just kind of reminds us, big picture, what we're doing in this question.